So now that we have discussed the large scale and large volume portion of our terrestrial Earth, we can focus on the surface of the Earth, the time, form, and formation. And so, form in terms of what was the big scale form, where are the continents, time, how much time it takes to produce these forms, and formation is the structures upon which are found on the form. So, with that, I want you to think about mountain ranges, deltas, levees, plateau areas, the plains. Those are what I mean by form. So, starting out with dating of Earth's history, we can date something two ways. We can date something relatively and we can date something absolutely. When we think about relative, think about like those little forms that you get that asks you, what is your age range? 12 to 20, 21 to 35, 36 through 40, 40 through to 55. That would be relative. Um, right now, I'm sitting at home in front of my computer and I'm relatively close to my desktop. I'm relatively far from you. So we don't actually have measurements. I haven't got a tape measure out to figure out the distance between myself and my screen. I don't have a tape measure or satellite data to measure where any of you are, but I know that I'm much farther from you than I am from my computer. So that's relative, all right? So we can do relative dating. Is it close in time? Is it medium in time? Is it far in time? Or is it way out there in time? Um, and absolute dating is providing a date or a range of dates within recognition of how much time has passed. So with this, I have two diagrams on this screen, the KT boundary and the Mount Mazama ash. And we know the dates of both of these. So we have absolute dates for KT boundary and Mount Mazama ash. Anywhere that you go where you can find either one of these two layers, you will relatively know that the stuff above it, this stuff here, because this is the KT boundary, and for Mount Mazama, this yellow or white line, pardon me, everything above it is going to be younger. So that's relatively younger than Mount Mazama and relatively younger than the KT boundary. Everything that's below KT and everything below Mount Mazama is relatively older. So those are two ways we can recognize relative dating. In these two, KT boundary is found globally. The KT boundary, for those of you who are dinosaur aficionados and nerds and just love dinosaurs, are familiar with this because it is the stratigraphic horizon. When I say stratigraphic, I mean rock layer that contains iridium, and iridium is found only in mass amounts extraterrestrial to the Earth. So they are coming to Earth through satellites like meteorites. So this particular layer came from a meteorite that was struck at the Yucatan Peninsula and dusted up so much matter from its impact that it spread globally. So everywhere that we go on the planet, wherever we find KT boundary, we know the date from that boundary. And on the next slide, I'll talk to you about how we can figure out dates. So KT boundary, everything below this is older than the last of the dinosaurs. And we find dinosaur remains and organic organisms which came before the dinosaurs. And then above this horizon, we're finding a few dinosaurs left behind. In fact, we're living amongst dinosaurs when we think about birds and crocodiles and alligators and other reptiles. But the volume diminishes. We had mammals below this layer. We have definitely mammals above this layer. But we have exchanged prominence. Prominent dinosaurs, prominent mammals. With the Mount Mazama ash is from a volcano, that erupted in northern Oregon, so Mount Mazama. And Mount Mazama today is Crater Lake. And the eruption from Mount Mazama was so great, it blew the top of Mount Mazama off, and it left just the caldera behind, which is now infilled with water and is now a lake. The ash from Mount Mazama was picked up by the westerly winds, which you're all familiar with now, and spread this ash across many western states and Canadian provinces. So anywhere that you go where this ash fell, you know that everything above this line is less than 5,000 years old. Everything below this line is greater than 5,000 years old. So to give you some specifics then with this relative dating, when we relative date something, we go by the law of superposition. And superposition simply states that the material on the bottom or the lowest layers is the oldest. And as you move upwards, each consecutive layer up is going to be younger than the last layer. So in figure A here, G is the oldest of all the layers, and F is slightly younger than that, and E is younger than F, and so on up to A, which is the most recent material which was deposited, regardless of the means of deposition. So it could be sand that is blown in from a desert. It could be sediment that's coming up off of a river mouth into a delta. It could be volcanic material deposited. So this is what you end up getting. Figure B in here is showing that these stratigraphic layers, nice way to think of a stratigraphic layer is like all of these layers together are a book, and each book is a chapter. And when you look at each chapter, you are reading the content of that chapter. You're reading, what was the material, under what conditions was it deposited? Can we tell if there were organisms that existed here? What type of climate occurred under these conditions? How old is this material? And usually most of us are afforded the opportunity to see stratigraphic layers through some sort of event that cuts into these horizons. And so each line each bed is a horizon. So we might see something like a river. In this case, it could be the Grand Canyon, and the Colorado River has cut and incised this down, and now we can see all the stratigraphic layers above hand. Most of us see this as we're traveling through on a highway, and we have a cut bank of the highway that was removed, so the steepness of the slope for the road isn't a continuously large gradient. So we're not traveling too steep uphill or too steep downhill. So we're able to be afforded this information in this regard. I want to note that sometimes there are disruptive events that will interrupt the law of superposition, where no longer the oldest stuff is on the bottom and sequentially we get younger and younger. But things like tectonic activity can push older rock above younger rock. So in this case, we're sliding this stuff above, and we might find that this older layer now is sitting at the same horizon line as this younger material here. Or it may get pushed over in something called a thrust fault, where we actually have older stuff sitting on top of younger stuff. So there are events like that can take place. In diagram D here, we have what's called an intrusion, where we've got some volcanic matter, which is younger, finds its way through some cracks and pushes its way through all of these older horizons. So in this case, this is the young stuff, and everything else is older than it, including this top horizon here. So again, stratigraphy is each individual layer of the rock, and it provides a record of the Earth's history. So what that rock was and what it's contained, or what it is made out of. So absolute dating then, we're able to analyze the materials in the rock to determine, how old, relatively speaking, something is. So we've got relative and absolute dating in the diagram here, and I've told you about law of superposition, which is on this side. So the absolute dating here is going to tell us how old something is within our ability to figure out a range. The big deal is when you're talking about a planet that is started to amass rock at 4 billion years, a couple million years one way or the other isn't such a great difference. Because you're talking about 4 billion years. So, getting down to 1 or 2 years almost becomes insignificant. Getting to 100 years, 1,000 years, 5,000 years is not really significant when you're looking at rock that is in the billions of years, the stuff down here. When you're getting into the younger stuff, the accuracy improves. So then you can get into a rock which may be a few million years old, but you can figure out the date to a couple hundred years. And then when you're talking about soils, you can talk about much shorter time periods. So with absolute dating, the big methods of dating is through radiocarbon dating. We can radiocarbon potassium, or most commonly, most people are familiar with carbon dating. And what's happening with carbon dating is when a rock layer, before it becomes a rock, is deposited on the surface of the earth, it has 100% of all of the, in this case, the U's stand for uranium. So all of the matter in it is radioactive at 100%. At a halfway point, the expectation is 50% of the radioactive material will have converted to its partner element. Take that time again, half it again, and now 3/4 of the material, which was once radioactive, it now is at 75% inactive, or the partner, and then 1/4 or 25% of the original matter. And it keeps halving this way. So then we go from a 25-75 split, then to like a 12-80, what is that, 88% split. I can't do math right now, 88% math. So we continue with half-life. So if we think about it another way, at time 0, which is this yellow one right here, time 0, I have 100% of everything. At time 1, this one, I have only half of the original stuff left. And we can, for this rock, we can assume, let's say 1 billion years went by. It took 1 billion years for half of it to convert. For the half that's left unconverted, it's going to take another 1 billion years. So 2 billion years goes by, and so on. So when we've got 1/4 of the material left, or half of the half that was left before, 2 billion years goes by. For 1/8 of the original material to be left behind, then we have 3 billion. If we're going to go to 1/16 of the material left behind, then we're at 4 billion. If we're going to go to 1/32 of the original material left behind, now we're at 5 billion. All right, so that's how radioactive dating takes place, and that takes a laboratory to figure that stuff out.